Okay, so let me remind you what we were up to last time. We've kind of artificially classified materials into two different categories, although we'll kind of loosen this and turn it into a continuum later. So right now we have conductors, which have free electrons, and insulators, which have bound electrons, and we're kind of looking at the consequences of what that means for their behavior. So that's kind of what I'll start off today doing, is by basically kind of showing you a bunch of phenomena. What does the conductor do? What does the insulator do? Let me remind you the few that I got to last time. If we put a neutral conductor into an external electric field that's uniform, the external, then it undergoes the process of what's called charge polarization. So some electrons go upstream, leaving protons downstream. And so the charge separates out. It's not all mixed in completely evenly. But the net force on this object will be zero in a uniform electric field. And the reason why, again, is because these minuses are in just as strong of an electric field as these pluses, so there's no overall pull on the object. It's a different story when we get over to a non-uniform field. A non-uniform field, as I've drawn here, this is the external. It gets weaker as it goes to the right. And then what we find is that after the charge polarization occurs, the minus is in a stronger region of field and is attracted into it, or upstream to it, I should say. The minus charge wants to go upstream more than the plus charge wants to go downstream. And so we wind up with a net force towards the region of stronger field. So if you have a non-uniform field, then a neutral conductor will be experience a net force. Now, what could be causing that? Well, here's an example. So what we find is that a neutral object can be attracted by a charged one. Okay? So that's the principle behind static cling. This idea that a charged object can attract neutral ones through this mechanism of charge polarization. Of course, it's far more normal for an object to make a non-uniform field. That's the norm. Uniform field is kind of unusual. So if any time you have a kind of a normal object, usually it makes a non-uniform field, and if you put a neutral object into that field, the neutral object will be attracted to the charged one. Okay? So that we talked about last time. And that's going to form the beginnings of a chart that I'm going to make for you. I'll keep it over here. This is the phenomenon. I'll list it over here. I'll say, what does the conductor do? What does the insulator do? So we're going to kind of add things to the list today. First of all, charge polarization. Does it undergo charge polarization, conductor? Yes, it does. Okay. Now, one of the consequences of charge polarization is attraction to a charged object with a non-uniform field. Most certainly. So I'm leaving those kind of as like one row because one really just follows from the other. So first, do you charge polarize at all? And then what kind of field are you charge polarizing in? So if it happens to be non-uniform, which is far more normal than not, then the object will actually experience a net force. The electrostatics lab, you saw that happen with the packing peanuts, right? You broke off little bits of that. Those little bits are neutral, and they attracted to charged things. If you forget to put in a dryer sheet in the dryer, you'll also notice this as well when you take out some clothes. Okay. Before I catch the insulator up, let me say a little bit more about the conductor. Now, we talked about the charge polarizing. Does that mean every single electron is on the left side and every single proton is on the right? Well, obviously not, because then you've torn it apart, right? There is no object anymore if you've literally torn the atoms apart. So this is not every electron, this is just some electrons, right? And the thing I want to address next is, well, how does it know how much to polarize? I mean, there's how many electrons have to go over there. And it turns out, just to kind of give away the punchline, enough electrons have to go over there so that no more want to go over there. Okay? So let's talk about the mechanism of how does charge polarization know when to finish. So when is charge polarization complete? How does it know when to stop polarizing? There are certainly more electrons in the middle here. They're just mixed in with the pluses, and we don't draw a bunch of minus and pluses if they're evenly mixed, because then we just have to draw everything just covered in plus and minuses, and that would take a while, right? So all in here, there are electrons. They're just interspersed freely with plus charges. There's no overabundance of them. When we put a minus over here, it just means there are more electrons than protons. When we put pluses over here, it just means there's imbalance the other way. So let's take a look at the process of charge polarization. Here's what happens. So we take the interior of the object. So let's say this is the interior. I'll mark that off. And the very first electron that we might take a look at, you can think of that as experiencing the full brunt of the external field. So the external field is quite strong. I guess we'll draw it like that. There's E external. And of course that's going to feel a force, right? And which way does that force go again? Left. Negative charges go upstream. So this thing will experience a significant electrical force. And let's draw it over here. So this is initial. And then let's draw it a little later. Now let me remind you that E external, first of all, that's still there. That's supplied by some outside mechanism. So that doesn't care about what's going on in the conductor. But now there are some electrons that have already gone to the left edge, and of course that leaves, since this thing is neutral overall, it had to leave behind a positive charge. So we have the beginnings of charge polarization, right? So these are charges that have gone earlier than the point I'm talking about, and now we're looking at how much does the next one want to go. So let me draw in the next electron. Now that one, it does also, of course, sense the E external and wants to go upstream, but can you see why it doesn't want to go as much there? It doesn't like this one, right? So electrons might like to go upstream to the external field, but they also don't like the fact that other electrons already beat them to it, right? So the way we can visualize this, again in the field picture, we can think that there's now a new electric field that's caused by the minus and the plus that went before. And remember, electric field lines point away from plus and toward minus. So I guess if I draw these in red, that might look like this. And I'll call that E induced. Okay? So I call it E induced because this is the electric field that's starting to form from the charge polarization. It would never have happened, of course, if E external didn't encourage it or induce it. That's why we call it E induced. So look at what's happening here. What's happening here is this. We have that E external, which let me, I guess, draw like this. Now that is constant, but E induced is starting to grow. So this is E induced, and this is growing. Every electron that went before is going to add a little bit of motivation to not do, for more to not go. In fact, we can think of E external plus E induced at this point. It looks like E external is still larger, so E induced might take a little chunk out of it, but E net might still go like this, right? So E net might still point to the right, and a negative charge that wants to go is still going to go upstream to it, but it's just not as excited anymore, right? Does that make sense? So while all the electrons want to go upstream to E external, the more electrons have gone before, the more E induced they've made, the more they're going to discourage any further ones from going, right? The field picture is just kind of a way to visualize that. If you're not entirely comfortable with fields yet, just think of it as every subsequent electron wants to go less and less because other electrons have already gone and it doesn't want to go join them, right? Negatives don't repel from negatives. And so, eventually, the final state, as you can probably guess, is that there's an equilibrium reached between these two factors. So what it looks like now is you still have E external, still points to the right. You have some even more electrons have gone. There's even more charge in the charge polarization. They make an even larger E induced. And if E induced cancels E external, what's the net field? It's 0, right? So if this, which is constant, E external, and this grows, then this can grow to cancel this, right? So now E net is equal to 0 because E induced has grown to cancel E external. And if the net electric field is now 0 in the interior, what will be the force on the next electron? 0. So this, the force is 0 now. So that electron will stay put. Enough have gone. So that is the end of the charge polarization. The charge will polarize only until the net electric field is 0 in the interior, which means enough electrons have gone to the left that no more want to go to the left. Does that make sense? Remember, the electrons in a conductor are completely mobile to do as they want to do. So the only reason why no more electrons want to go, it's not like they're stopped from doing so, but at this point, no more want to go because enough have gone, right? And they discourage further ones from going. So, let's add to our chart here, E net inside a conductor is actually 0. We give a name to this phenomenon. We call it shielding. We call it perfect shielding. Perfect shielding. Now I guess let me give you a few particulars of the situation, and that'll really kind of inform why they call it perfect shielding. Now you're just going to have to believe me on this because I can't do the numbers here on this calculation, but here's what I want to tell you about this process. From the process of the first electron starting to polarize to finishing polarization and no more wanting to polarize, no more wanting to move, this process is basically instantaneous. So it happens very quickly. And as far as how many electrons need to polarize in order to shield the rest, well, it turns out as the number of electrons that are available in even a normal chunk of material is vast. Okay? There's billions upon billions upon billions of electrons. There are tens of thousands of coulombs available. It's just, of course, in a normal object, they're of exactly equal amounts, and that's why it's neutral. But there is a tremendous amount of electrons available. So it turns out that for a very few electrons, a very small percent participate in the charge polarization. Because that's really all you need to cancel off even a relatively strong E external. Any object barely has to lift a finger to move a very small percent of the electrons, and then the induced field is able to cancel off the external. Okay? So what that means is that if you're one of the electrons in this object that's actually participating in the polarization, that's like winning the electron lottery. Okay? So that's something that very few electrons will actually be a part of. The vast majority of the electrons in the interiors are, say, external field. What external field? I'm not aware of any external field. They're being shielded from that external field by the very few electrons which have polarized. And basically, when those electrons polarize, the E induced of those few cancel E external, and the vast majority of electrons in the interior have no idea that E external ever is even there. Okay? They're shielded from its knowledge of it. Okay? So it's like, you know, when you're walking with a little kid down the street, right? And you see some kind of weirdo, and you kind of just like, hey, let's not go over there. Let's, you know, you kind of, the kid never knows that you're trying to get them to go somewhere they should, right? That trying to keep them away from somebody. So that's what we call this perfect shielding. The vast majority of electrons in the interior have absolutely no idea that E external is even there. Okay? So hopefully you see the mechanism by how which that is possible, and then you take these few facts here, which are, I of course didn't justify, to kind of understand why the most electrons don't experience any force at all. Okay? Now, let me tell you about an extremely useful application of this. Okay? So, as I kind of go along here, I'm going to try to give you some ideas on what this stuff is practically useful for. Okay? So, what's a practical use of shielding? Practical use of perfect shielding. Well, let's take a lightning storm. In a lightning storm, you have charge buildup in the clouds. It can be plus or minus. I think one is more common. But let's say it's plus. And it turns out, for reasons that will, well, I guess I can mention it right now. Basically, that once you have charge buildup in the ground, it actually causes a charge polarization on the Earth. I guess you can imagine this Earth is a big sphere. So basically, that's kind of what happens. So the Earth charge polarizes in the electric field of the cloud. So long story short, this kind of acts like a parallel plate capacitor. So the electric field kind of looks like this. And so that is an external field. It's a very strong external field. In fact, it turns out that this external field can be so strong that if you take a look at an average air molecule has both a nucleus and some electrons around it. And it turns out that you can break apart that marriage of the positively charged nucleus and negatively charged electrons because they are both more attracted to the opposite charge in the cloud and ground than they are to each other. So that's a phenomenon which we'll discuss around homework number 4 called dielectric breakdown, which is commonly, in this case, known as lightning. It's when you're literally tearing the air molecules apart. So obviously, it's a very strong external field. You do not want those the molecules being torn apart to also include those in your body. Okay? You do not want to be struck by lightning. So one of the safest places that you can go in a lightning storm is into your car. And that has nothing to do with the fact that it has rubber tires. It has to do with the fact that you're surrounded by a conductor. Okay? So you can take advantage of this perfect shielding. So if it's you here in your car, I'll just draw it as a box. The important thing is that even though it's not a solid chunk of metal, of course it's a contiguous piece, which means that if an electron wants to go from any spot on the outside of your car to any other spot, it can get there, right? There's no impediment to going wherever it needs to. So what happens is, if you're in a very strong external field, you will have that there will be a pileup of electrons on the top. In this case, the electrons go upstream. And the positive charges, of course, are left behind. And so this creates an E-induced. So E-induced. Now, even though the electrons are flowing around the outside, the electric field they create can easily, the induced field will connect them and can go also into any cavities, like the one you're sitting in, right? And so what happens, how many electrons polarize? Well, enough so that E net is 0 in the interior. Perfect shielding. So basically, you're taking advantage of the fact that there's a vast number of free electrons in the body of your car, which is conducting, and they will flow in such a way to protect you from the external field. Okay? So I posted for you in WebAssign some links where I show you this, one of which is literally this. Someone sitting in a cage. It doesn't actually even have to, be mostly solid like a car. It's actually a cage with just some bars. It's mostly air. But it's a cage that's all around the person so that electrons can go from any part of the cage to any other part of the cage on the outside to create this charge polarization. And they basically send a man-made lightning bolt hitting this cage, and the person inside is just fine. They even touch their hand to the interior. Okay? There's a couple bars, metal bars here. They're touching the interior, and the lightning bolt is hitting right there. Okay, so you can check that out. That's from the Boston Museum of Science, where they make some of the largest man-made lightning bolts that you will, I think, in the world. And whatever it is, 3 or 4 times a day, somebody gets in the cage and gets hit by it. Okay. I also posted some links to a guy named Dr. Megavolt, who takes the concept even further and wears a cage around them. So they walk in a metal suit and get zapped by lightning. They're totally fine. They can even, he even jumps in the air. You can see the lightning bolt hit his head and come out his feet and into the ground. Okay, so this is the perfect shielding. Okay, does that make sense? Yeah.
What if the electric field inside the box is not strong enough to cancel out?
Right, so that's where we take advantage of the fact that there's a tremendous amount of electrons available in anything. So the electric field that would be so strong that you'd run out of electrons is way more than you would ever see in any kind of practical situation. So there's a vast store of electrons that are available to participate. Even if you want to cancel off a tremendously strong E external, it's still a tiniest little percent of electrons. It barely needs to lift a finger to be able to cancel it off. You're just not going to run out of electrons to do this. So that's the mechanism by which charge polarization happens. Because in a conductor, charge is completely mobile, the only thing that limits the electrons from stopping polarizing is they don't want to anymore, right? Because enough have already done it, so no more want to go. So the next thing that I want to address is to kind of catch the insulator up. Okay, so the insulator, I haven't really filled it in yet. Obviously, it can't work the same way in an insulator because the electrons can't just move around however they want in an insulator. They're bound to a particular nucleus. So let me take a look at that. So let me put a neutral insulator in an external field. So in the insulator, we have a positively charged nucleus, and we kind of think of the negative as not being free to roam anywhere it wants to along the object. It's kind of tied down or owned by that particular nucleus. So really the only freedom it has is to kind of choose which side it hangs out on, right? So the electron can't wander far, but it can kind of choose which side of the nucleus to be more on. And in this case, it's a no-brainer. Of course, the electron would want to be upstream, right? It want to follow E external, but that's as far as it can go, right? So if we were to draw a bunch of atoms on this, we'd find, inevitably, that the electrons would kind of all be, on average, to the right. I haven't drawn the whole thing in, but you get the picture, right? So here's my analogy to describe this. So if you have an ice cream truck coming through the neighborhood, all the kids that can are going to run to the ice cream truck, okay? So that's like the example, okay, up here, this ice cream truck, the electrons are going to go, right? Electrons like to go upstream to a field, kids like to go to the ice cream truck, right? But let's say you have some kids that are grounded, okay? They're not allowed to leave the house, okay? Well, you still know where in the house they're going to be. They're going to be looking at that window out at the ice cream truck. Oh, I wish I could go out there, right? So that's what these electrons here are doing, right? We're going to find them more on average upstream. Now, this may not be anything to note, but let me point out that the interior here is still a mix of plus and minus charges all mixed in. I usually don't bother to write that. That's just stuff in general. But now, because they're not all in random orientations, I do find that there's more negatives on the upstream side and more positives on the downstream side. So we actually have charge polarization still, okay? So we still have charge polarization. The only difference is that it's not as much, right? So it's not as much because we're relying on just atomic rotation, so I guess atomic reorientation, versus my actual migration of electrons in a conductor. So we're kind of limited by the fact that we have atoms that are kind of rotating, that are reorienting near the surface. That's where our minus charge is coming from. We can't just have as much charge going to the left, as many electrons going on the left edge as we feel like, or until they feel like stopping, right? We're kind of limited in their availability. So that's where it comes that the insulator kind of tries to do everything the conductor does, but not as well, because it doesn't have access to this mass migration of electrons. It can only just charge polarize by reorienting the atoms. So if I go over here, can the insulator charge polarize? Yes, but not as much. And, of course, does that mean it can attract to a charged object in a non-uniform field? Yes, but not as much. So everything is kind of, I want to do it too, but can't do it as well, okay? And by the way, I should point out in lab, you guys were charge polarizing little bits of packing peanut, which by most people's measures are insulators, okay? So you saw it work just fine in the case of an insulator, right? It's not as strong as it would be for some conductors, but packing peanuts are also very light and fluffy, so you can notice the effect. Okay? So even though you don't generate much attractive force, you can actually still pick it up because it doesn't weigh there. Those bits don't weigh very much. In fact, one of the first things we ask you to do if you can't pick up a whole peanut is to break off a little piece. Right? All right. Now let's catch up with the E net inside. Well, this process that we discussed is obviously not going to work from beginning to end because this whole process was this idea that electrons polarize until no more want to go. For an insulator, it stops somewhere in the middle. Okay? So an insulator, that's kind of the end of the line. So at some point, when you've charge polarized a little bit, well, that's all you can polarize, right? And so if that's the case, E induced is something, but it is not able to grow until it cancels the external. It just kind of stops around here. Now you may be wondering, well, doesn't this negative charge want to go upstream? Well, sure, but remember that that negative charge in the middle somewhere is still attached somewhere, right? So it can't just go to the left. So what happens is we have something called partial shielding. So to recreate the graph, just so that it's not all on top of each other, you have E net, or sorry, E external, which looks like this. You have E induced, and E induced is limited from growing. It can't grow very much. So E induced is limited by the charge polarization. You don't have as much, so you don't have as much E induced. The net field will point in the original direction, but it won't be as much. Okay? And that, by the way, is what holds all of the atoms in the interior into this orientation. So the negative charge would still want to go to the left. It won't actually go to the left because it's bound. So if we fill in this chart, perfect shielding, this is partial shielding. So E net is going to be less than E external. So we call it partial shielding. And I'll tell you right now, how much can E net be reduced by? Well, it depends on the material, but oftentimes it's small constellation that E net might be not very much smaller than E external. So if Dr. Megavolt, for instance, were to accidentally put on an insulating suit, he might get killed slightly less than he would without anything. But again, if E external is big enough that even if E induced can take a little bit of away, E net can still be really big. If you, E net is going to be smaller than E external, but if that smaller thing is still too big, then you've got problems. Okay? In fact, in that case, if E net is too big, this electron will not only feel a force to the left, but it will get pulled off. Okay? So again, we'll do the details of that later. That's just something called dielectric breakdown. That's when you can literally pull a piece of insulating material apart. So you make those bound electrons not bound anymore. Okay? So that's what we have, the net electric field inside. In a conductor, the E induced can grow to perfectly cancel off E external, and then it just stops. It's self-limiting. Here, you're limited in your ability to charge polarize because the electrons aren't fully mobile. E net is smaller than E external. So we have something called partial shielding. It's going to turn out that partial shielding, we're going to save that for later. It has no apparent use yet. This we talked about as being good protection from a lightning storm. Another, by the way, application of perfect shielding, if you've ever ordered an electronic component that's sensitive to static electricity through the mail, it'll come in a special conducting bag. And that conducting bag is basically shielding the component from the outside world. This has no apparent use whatsoever, but we will find a use for it. In fact, it'll find use in an electronic component called capacitor and make it better. Okay? So we'll get to that around homework 4. Just give you a little bit of a preview. Okay, are there any questions so far, by the way, before I move on? Okay, so a lot of conceptual stuff right now, not a lot of calculations. You'll find some conceptual questions on the beginning of your homework number 2. And this is also the stuff that's really kind of made for the multiple choice section of exams, right? Just kind of asking you what's going on in general, not asking you to calculate anything. The actual calculations involved in some of this stuff are beyond the scope of the course. So, the next order of business is to look at E net on the outside. So let me go back to the conductor. Let me go ahead again and put it in a uniform field. So there's my E external. And I guess let me do the neutral conductor in a different color. So neutral conductor. Let me do it in green. We know that a charge polarizes. Minus is upstream, plus is downstream. So let me draw the electric field induced. And then here's the thing. We said it's on the interior, it goes like this. E induced. It points the opposite way of E external, and that's why they cancel, right? But I can't stop there. These charges, these plus and minus charges, are not obligated to only make electric fields in the interior. They, of course, make them everywhere. The closest electric field map to that is the finite parallel plate capacitor, right? It's, I talked about that a lecture or two ago. So if I were to draw the electric field, it probably looks like this. That is E induced in its entirety. Again, it's closest to the finite parallel plate capacitor. In between, the field is basically uniform. But then as you start to get out, it starts to have this kind of loopy shape. Okay? Now, it's easy on the interior because it's a one-dimensional addition, right? E external points to the right, E induced points to the left, they cancel, that's it. Outside, this looks like a nightmare, right? So this is the kind of stuff you're contending with on your homework 1. Like, for instance, right here, if I wanted to find the net electric field, I'd have to do the vector sum of these two, right? So I'd have to add this, which is E induced, to this, which is E external, right? Find E net. If I had to take a guess, maybe, I don't know, maybe like this. That's just a guess. That would be like E net. I could do it somewhere else, right? Somewhere else, maybe right here. Let's say at this point. Again, I'd have to do a vector addition of E external. That's at least always to the right. But E induced is all over the place, right? It looks like this. And so if I had to guess, again, they both kind of look maybe something like this. That would be E net, okay? Now you can see that my guesses here have a large possible source of error because I don't really know the numbers, I don't really know how long the arrows are that are contributing. So this is not going to get us anywhere, okay? I have to do every point all around, and that's working smart. That's working harder. Let's work smarter instead. So we can do a little bit of a thought experiment and figure out something very generally true about what the E-net looks like, and we'll just go with that. So here's how I'm going to do it. So what does E-net look like outside a conductor? So in order to convince you what it looks like, let me grab a section of the conductor. So this will be outside, and this will be inside. And let me grab one. Let's say it's like a picture of this electron right here. So it's a little zoomed in view of this electron. So I'm looking at an electron like this. So there's one of the electrons that's in the charge polarization. So it's come to the surface. Let me tell you what it can't be. So this is one of, I forget there's a name for this kind of proof. I'm going to assume something. I'm going to show you why that's ridiculous, and therefore it must not be like that. It must be like this instead. So I'm going to suppose E-net comes in like this. I'm going to show you that can't be. What is this E-net? Well, this E-net, of course, is E-net is E external plus E induced and just in case I want to drive this point home, so we talked about if you make an electric field, you're not eligible to feel a force back on yourself, right? You can't feel a force from your own field. That's just violating cause and effect. You can't pick yourself up and carry yourself out of the room. The electric field you make is eligible to act on other things. So if that's the case, you might think that I've broken my rules here, because this electron is one of the many electrons that is making E induced. So if you want to be technically correct, this is an E induced from all the other charges in the charge polarization except this one, okay? So hopefully that's okay, right? If I take one little measly electron out of all the charges in the charge polarization, E induced is basically still roughly the same, right? All right, so this is basically how this one electron is being affected by its entire environment. Whatever that external field is and all the other charges in the charge polarization. So electrons, which way do they feel a force with respect to the field that they experience?
Upstream.
Upstream. So this would feel a force like this. Now here's what's wrong with this. That force, I can break it up into two components. Force parallel to the surface and a force that's perpendicular to the surface. So for instance, if we imagine the interior of this room as the interior of the conductor, and this is my electron, right? So this is an electron that has gone to the surface, so this is the inside surface. It can't get out of the room, just like it can't jump off the object. Now, if it feels a force that's perpendicularly outward, well, it can't go there, right? So it can't just jump off the object. But if it feels a force parallel, well, you can skim along the inside surface just fine, okay? There's not that there's anything wrong with that, but that means that it's still going to be moving, okay? So this is fine. It would cause it to skim along the inner surface. Whereas F perpendicular, it couldn't do anything with that. So for us, we're not interested in the politicking of how all these electrons get settled in the charge polarization. We assume that charge polarization is approximately instant, and when it's instant, that means that everybody finds their places and they find where they like to sit, and then they stay put. The charge polarization doesn't evolve with time, it just is what it is. So the charge polarization is approximately instant, which means that all of the charges find their spots. essentially very quickly. And we have achieved an equilibrium situation. And if we've achieved an equilibrium situation, it means that whatever desire they have to skim or skirt along the inner surfaces to redistribute, they've already done that. And if they've reached equilibrium, F parallel has to go to 0. If it hasn't gone to 0 yet, it means it hasn't yet found its spot. And we're assuming that that gets taken care of very quickly and we don't worry about it. So what I'm trying to tell you here is that if F parallel goes to 0, what we're forced to conclude is that E parallel has gone to 0. There is no component of the electric field anymore which would tend to make that happen. So what have I just proven? I've proven by counterexample that E net will end up being perpendicular to the surface on the outside. Now, that's actually in agreement with what I've found. Notice that these are both happen to be perpendicular. But I've been able to reason out why that is. In fact, let me go ahead and draw a cleaner version of this. So my cleaner version is going to have only E net. So it's going to be E external, which is uniform, plus E induced, which is all this crazy stuff, this dipole thing, etc. I'm just going to tell you that the sum of that, I didn't leave myself enough room, let me move this a little bit down. Here is what the net result is. This is E net now. This is the sum of these two, which is E net. I guess I should draw the charges, minus and plus. That is the net electric field. Inside, it's 0. We already knew that. And this drawing allows me to show you that the outside, it's bent perpendicularly to the surface. This electron, the only desire it has left is to go upstream to that field, but since it can't do anything with that, then it's found its spot. This electron, it would like to go this way, but it's found its spot, so that's it. And this one would want to go that way, right? But since it can't go that way, that's the end of the charge polarization. This is the equilibrium situation. So what we have is that the net electric field outside a conductor is bent perpendicular to the surface. Now that's locally where E induced matters. I should mention out here, E net, which is E external plus E induced, starts to look strikingly like E external on its own, and that's because this is starting to not matter, right? E induced is strongest near the conductor. It gets weaker and weaker and weaker as you get further away from it. Whereas E external is uniform and never dies. So out here, they're basically the same thing. So again, when you're far away, E external basically dominates. When you get closer, E induced bends the net field perpendicular to the surface. These are all perpendicular. And then in the interior, E induced shields the interior from E external. Okay? So, again, let me try to let me catch the insulator up. Well, insulator can't charge polarize as much, so I should say it gets bent, but not as much. So it tries to do everything the same as the conductor, but it just doesn't have as much access to do it. So it bends the field a little bit, but it can't bend it quite as much away from uniform. It can't bend it all the way perpendicular to the surface. Let me try to again show you some practical usages of this stuff. Okay. So this, just so you know that this is not just abstract stuff to torture you. This is very practical consequences. Are there any questions on the reasoning here before I clear a little space? Okay, so let me show you a very practical consequence of this. I'll draw a conductor, a neutral conductor, only this one's going to be really funny shaped. It's going to be a ball like I normally draw, and then a huge spike on it. Okay? So it's very slender, needle-like kind of proboscis, I guess, sticking out. So let's say I put that in a uniform field. So I put it in the same uniform field that points to the right. Well, if the electric field lines are going to get bent perpendicular to the surface, so I'll put the charge polarization in here, minus, 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 plus, 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 plus. And if that's going to get bent perpendicular to the surface, try to draw that. Trying. Looks like this. I think I have a line missing, but that's. You can draw some on the other side as well, I suppose. Now let me ask you this, where is the strongest electric field? My drawing is poor, but it's supposed to be here, at the point. So if you have to bend perpendicular to this kind of extreme geometry, it tends to focus the field lines. It's not surprising that the electric field is so strong because the charge polarization here, there's a lot of minus charge in a very close space. So electric fields tend to be very strong on sharp conducting points. This premise is used to build something called a lightning rod. Okay? So the electric field net is very strong near sharp points, and we can use this to build what's called a lightning rod. So a lightning rod is something you stick on top of a building, and a common misconception about them is that they're there just in case lightning strikes. Well, it's more likely that lightning will strike there because you put it there. But it's also somewhere where you're prepared for it. You run a line from the lightning rod all the way down to the ground where if any charge hits it, it can run down and harmlessly into the ground instead of into somewhere where it would do harm. So what happens here is that the electric field is strong there, and that is where, if an air molecule is going to get torn apart, it's going to get torn apart there first. That's what lightning is. In fact, lightning forms when there are things called streamers. These streamers are places where the field is stronger, right? The field is not really uniform. It's stronger in certain places. And so the air molecules kind of start getting torn apart, and then when those two streamers meet, so basically finds a path through there, from the cloud to the ground where there's the stronger field, and when it connects them, that's when lightning triggers, right? It has a chance to go all the way from cloud to ground or vice versa. So you're actually encouraging lightning to strike there by starting this streamer of particles that's starting to break apart. Okay? And the way you're doing that is because the electric field is stronger near that point. Okay? So you're actually encouraging lightning to strike there. Does that sort of make sense? Okay, so lots of tall buildings and tall structures have these things, some kind of very sharp metal conducting points to encourage lightning to strike there. Okay. Okay. So the final order of business we have is to fill in one more row here. Doing a process called charging by induction. Are there any questions before I move on to that?
I guess I just don't really understand like why the geometry of it changes the electric field. Is there like more electrons in the point?
Yeah, you can see that if you're going to polarize this, and you're polarizing it onto this very slender thing, it's just putting a lot of electrons in proximity to one another. So E induced tends to be very strong here, or have to be very strong, until these net field lines are bent perpendicular to the surface. So really, the reason why the electric field is strong here is entirely due to this induced charge, right? Because remember, the external is the same everywhere. So the only reason why the net field would be stronger in one place versus the other is because of the induced charge. So here we have the negative charges in very close proximity, creating a very strong field to add to the external, whereas over here, the plus charges in the other half are able to spread more apart because the geometry isn't so spiky. One of the pictures I posted for you in WebAssign is showing you what happens if you take a parallel plate capacitor which has a nearly uniform field and then sticking a spike on one of the plates, and you'll see that it tends to kind of almost seem to gather the field lines. That in order to bend perpendicularly, it creates a very strong field. My drawings are just not very good, so that's why I posted some more computer-made things, so you can kind of see why having these sharp points tends to make the electric field lines bend perpendicular to them, and why that makes them generally closer together. Okay. Any other questions? Okay. So charging by induction, as you can guess, the point of this is to charge something. Now, we already talked about one method of charging called charging by contact, where you literally rub two things together. You guys tried this out in your electrostatics lab. But this is a way of charging something without ever touching it to another object. You might seem like that's impossible, but it's in fact very possible. Here's how it works. So charging by induction. You have a neutral object. It's actually going to have to be a conductor, and it'll become obvious why. And that is the object we seek to have a net charge on it. So we want more protons and electrons, or vice versa, overall. Here's how we do it. We bring any charged object nearby. Let's say it's plus charged. And by the way, that does not matter if it's a conductor or an insulator. That can be anything. Its only job is to be charged and to be nearby. Okay? All right? So what happens? Well, we know that the neutral conductor will charge polarize in the presence here, right? So it'll be minus, minus, minus over here, some plus over here, but that's not charged yet. That's just charged polarized. There's still, that object is still neutral. In fact, let me label these. I'll call this A and B just for reference. So B is still neutral, but at least now the charges aren't all mixed in willy-nilly. You'd have to get a pair of atomic-sized tweezers to sort them out. Now we do have overall minus charge on one half and plus charge on the other half, right? So step one in charging by induction is bring A nearby and B charge polarizes. So now we kind of have a grab bag where we have at least more minus charge on one half and plus charge on the other half. Now we just have to ditch one half of that charge and we have a charged object. Here's how we do it. What we do is we connect B to ground. That is the symbol for it. What do I mean connected to electrical ground? I mean literally connected to the ground, the earth. A big neutral object, okay? So now we connect B to ground. The earth, which is a big neutral body. Now the earth, because it is a big neutral body, it will basically be a source or sink for charge as needed. So if we want, we can ditch a bunch of charge into the ground, and it's still basically neutral because it's dispersed along the entire Earth. So if we send a bunch of electrons into the ground, well, they're basically gone. The Earth is still neutral. And likewise, if the Earth can also supply a large number of electrons, but still be basically neutral. So the Earth is basically a source or sink for charge while remaining neutral. We can get charge or send charge to the ground as needed. It'll still be neutral because it's very big. So what happens in this case? Well, in this case, what we have, electrons can come up from the ground. They're attracted to these positive charges, and they just join up, and that's how we neutralize the minus charge, or the charge on the right side. Okay? So when we connect B to ground, the half of the charge polarization is neutralized. Now you might be asking about the other half, right? This minus half. Now you might think, well, shouldn't they take the opportunity to repel each other? I mean, they're stuck there on this object. The object is now negative overall. Why wouldn't they repel each other and go into the ground? Why wouldn't we wind up back with a neutral object? Well, they're a little preoccupied, really liking this positive charge over here. So they're not going to do that. So here's the catch. We have to finish this up in a way to make sure that we retain that. First, we remove the ground connection, and then we remove A from the vicinity. So first, we take away the bait. Or sorry, first we remove the escape hatch, and then we take away the bait. Okay, so that's the key order. If you mix up steps 3 and 4, you won't get what you want. So what you will have at the end is this. Those minus charges now form the charge on this object. They will, of course, not all stay on the left side once you remove A, because that was why they were hanging out there in the first place. So now they're all spread out. And, of course, if they repel each other, the furthest they can get away from each other is be on the outside, right? They're cursing themselves, why didn't I escape when I had the chance? But you did remove the ground connection before you took away A. Question?
So if you were to brought a negative object for A, you would wind up with a positive B?
That's exactly right. So the charge that you get in charging by conduction will always be the half of the charge polarization that's attracted to the charge object, right? So you neutralize the back half while this half that's attracted here is kept around. And so you'll always charge B opposite to A, right? Because that is ultimately how you are getting the charge on your object, is you're taking the part of the half of the charge polarization that's attracted to your object that you bring nearby for the bait, and then you cancel the other half with the ground, okay? So that is called charging by induction because we never touched A and B, right? A just is in the vicinity. It plays a role, to be sure. It charge polarizes the object. That means that all of the plus and minus on that object is no longer intermixed, it's separated. Then we connected this object, sure, to something else, the Earth, but the Earth is also neutral. So we connected a neutral object to a neutral object, but because this was in the vicinity, we were able to get some net charge on B at the end. Okay? So charging by induction, that's how it works. You'll always wind up with charge opposite, the one that the charge object you brought nearby. And in this case, we have to say we can't really do it with an insulator. And here's why. We've really only connected this ground connection at one point, but once the electrons flow up, they have to be able to flow anywhere to neutralize the rest of it, right? So we need charge mobility to be able to cancel this off, right? So we're only connecting this to one point, and you want to be able to get onto that object from that one point and go anywhere as needed, right? So this is one of the things where the insulator just won't be able to do it. We need charge mobility. We're only connecting the ground connection at one point. And once charges come in and out, they need, from that point, they need to be able to go wherever needed from there. Okay? Are there any questions on charging by induction? Yeah?
How is it that you connect the object to the ground exactly?
It actually doesn't matter where you connect it.
No, I mean, what do you use? How do you do it?
You usually just take a conducting wire and just sink it into the ground.
Just on the side
It doesn't. It actually can be anywhere on here, surprisingly. And the reason why is that everything can always shift over to accommodate, right? So if you were even to connect it here, you might think, how is that going to work? Well, this can shift over, right? So electron can come up from the ground and replace this one, and the one that used to be there goes over here, right? So it all shifts around to accommodate the same goal. If you're asking how do you connect to ground in a practical sense, a lot of times if you're an electrician, you'll just tie it into something that you know goes to the ground, like some big, like a pipe or something that goes into the ground. A lot of times, if you can use even the chassis of your car is a big enough neutral body from some applications, so you use that as your ground. It's just some big neutral object. Any other questions? Okay. So now you have two ways to charge things. You can charge it by contact, a triboelectric series, or you can charge it by induction, if it's a conductor. Okay. So that takes care of the conceptual side of your homework number 2, and we'll be revisiting some of these ideas, especially partial shielding for an insulator later on, as I indicated.